In this goal, we're going to be talking about intermolecular forces. These are the forces that cause molecules to be held together in a liquid or a solid. They are quite weak when compared to covalent and ionic bonding. So what puts the atoms together is very, very strong, whereas in between the molecules, these are very weak forces. These weak forces are called intermolecular forces, or IMF. And even though they're weak, they influence the temperature of the boiling point, of the melting point. They influence the vapor pressure above the liquid, and they influence the surface tension. The first type of intermolecular force are called van der Waals forces, and they describe the force that is in between the two molecules. And I like how these are named because in the name, it describes what each molecule is. So for example, this first one. So we have our first van der Waals force is called dipole-dipole. A dipole has two poles. And what that means, it just means that it's polar. So this is the force between a polar molecule and another polar molecule. And we can represent the polar molecules as in the diagram down below here. So in your polar molecule, it has a positive side and a negative side, and in that solid or liquid they will line up so that we have opposite charges next to each other. And so just some different arrangements here, but what is the force in between this is called dipole-dipole. All right, our second intermolecular force is the dipole-induced dipole, and this occurs between polar and nonpolar molecules. So a polar molecule that you should know is polar is water. So water right about around the oxygen, it's a little bit positive, excuse me, a little bit negative, and right around each of the hydrogens it's a little bit positive. So this creates a polar molecule. And let's compare it to oxygen. So oxygen gas is nonpolar. So we have two oxygens bonded together and they are sharing their electrons. So dipole-induced dipole occurs when the polar molecule gets close to the nonpolar molecule. So separate, they'll each be polar or nonpolar. But if they come in close proximity, the electrons that are over here in the oxygen molecule, as they get close to water, they are going to be repelled and they will flee to the other side, so to speak. And so you will end up making a temporary polar molecule. So this is what induced dipole means. So again, it will stay this temporary polar molecule until the water is further away. And then it will go back to being nonpolar. So the stickiness in between the two molecules, this dipole-induced dipole, that is the attraction of the positive of this oxygen molecule to the negative of the water. And so that is your dipole-induced dipole force. And our third van der Waals force is called dispersion force. It is also called London forces, or you can call them London dispersion forces. What is happening here is we have an induced dipole and then an induced dipole. So that is yet a third name for these, induced dipole, induced dipole. So if we look at our neutral nonpolar molecule here, so very equal sharing of the electrons, and so the electrons are evenly distributed. But for whatever reason, for a split second, the electrons might get stacked up on one side. And when that happens, we create a temporary dipole. And if it's in close proximity to the next molecule, it will cause that one to be a dipole or a polar molecule. And so this will spread throughout the whole liquid or the solid. And so this will hold those nonpolar to nonpolar molecules together. In nonpolar molecular solids and liquids, this is the only force that is holding them together as a solid or a liquid. And every molecule, not just nonpolar and nonpolar, has these dispersion forces because every molecule has electrons. And so those electron densities can shift over. When they do that, they may cause a little bit increase in polarity, especially if it's nonpolar to begin with. So this can occur in just atoms. So our noble gases are just an atom and they have an evenly distributed electron cloud, but for whatever reason, those electrons can get stacked up, maybe on one side of the atom, and this creates a temporary dipole or temporary polar molecule. And then if it's in close proximity to another atom, then it will influence that to be a temporary polar molecule. And so then they'll stick together. And then this is the dispersion force. This can also occur in really small molecules, such as a hydrogen molecule. So hydrogen molecules only have 2 electrons, and so they are evenly distributed. But for whatever reason, if one happens to get more on one side, then you can create this temporary dipole. So these are constantly shifting, so they don't just stay like this forever. So they're constantly shifting around. So what might be the negative pole on one side of the atom in the next split second might be on the other side. And so it just kind of depends. These are constantly shifting and they're constantly influencing each other. So we end up having this shifting of these electrons, the shifting of positive sides and negative sides all throughout the material. And this is what's holding that liquid and that solid together. Okay, here we are with our second intermolecular force, type of intermolecular force, and it's called hydrogen bonding. So even though it's called hydrogen bonding, it's not a bond. So I wish they would find a new name for this, but it is not a bond. It is still an intermolecular force. So this is the strongest of the weak forces, as long as you're comparing about the same size of atom or of molecules. And this is a very, very specific dipole-dipole. So you do have to have a polar molecule to have this hydrogen bonding. It only occurs when hydrogen bonds with fluorine, oxygen, and nitrogen. And so I call these H-Fon bonds so that you can remember. If a molecule doesn't have a fluorine, oxygen, and nitrogen, and then that also has to be bonded to hydrogen, you will not have hydrogen bonding. So it's very, very, very specific. So water has hydrogen bonding because we have an oxygen bonded to a hydrogen, and in fact 2 of them. So what is happening here is oxygen along with fluorine and nitrogen are so small and so electronegative that they will take the electron from hydrogen a lot of the time. So it's still being shared, but it will be taken away a lot of the time. Well, what is in a hydrogen atom? A hydrogen atom only has an electron and a proton. And so if that electron is taken away, all that's left is a proton. And so it has what I call bare naked protons hanging off the molecule. These are intensely positive. So again, these are those naked protons. So the hydrogen bond occurs between the oxygen or fluorine or nitrogen of one molecule and the hydrogen of another. So this right here is the hydrogen bond. So notice what it isn't. It's not between 2 hydrogens. It's between the very electronegative atom, fluorine, oxygen, or nitrogen of one molecule and the hydrogen of another. So let's do some practice of determining what is holding these molecules together in a solid or liquid. If a second molecule is not mentioned, then we know that the molecule is just going to bond to another one that's just like it, bond to itself. So you first should determine if the molecule is polar or nonpolar, and then you should list all the intermolecular forces. And then we do want to indicate which of these is going to be the strongest of your set. So let's look at the first one. So this is ammonia. You should know this molecule. So NH3. And I'm just going to sketch this out. I'll sketch one going one direction and then one going the other direction. All right, so let's look at both these ammonia molecules and let's determine if they're polar or nonpolar. And we see that this is a trigonal pyramidal shape. Trigonal pyramids are always polar because they have that unbonded electron pair. So let's list all the intermolecular forces. So the intermolecular forces here, first of all, they all have dispersion. every molecule, because they have electrons, has these dispersion forces, or those shifting electron clouds. The second thing that they have, because it's polar to polar, is I have dipole-dipole. Again, I really like how it's named, because it's just named after what the polarity of the molecules are. And anytime you have a dipole-dipole, you need to double check and see if it has hydrogen bonding. And we see that we do have nitrogen bonded to hydrogen, and so we do have hydrogen bonding. So I'm going to attempt to kind of sketch these intermolecular forces so you can imagine what they look like. And I'm going to start off with the hydrogen bonding. So again, the hydrogen bonding comes from the bare naked protons, and all of these hydrogens will have them because nitrogen is such an electron hog. So you get hydrogen bonding between the nitrogen of one molecule and the hydrogen of another. And so I can put that a couple of places between these two molecules. All right, let's work up. Let's look at the dipole-dipole. So the dipole-dipole has to do with looking at the negative ends of molecules and the positive ends of molecules. So let me just sketch these out. So you're going to have that dipole-dipole force that will run between these two molecules. Okay, with the positive ends and the negative ends. Kind of a simplified version of this would be, again, lining up those positive ends and those negative ends, and the force in between, that is your dipole-dipole. Last but not least, we have our dispersion forces, and our dispersion forces again have to do with shifting electron clouds, and so that will just be layered right on top of all of these. Okay. Now, what is the strongest intermolecular force? And that would be the hydrogen bonding. So when you're just comparing in the same molecule the different strengths, the hydrogen bonding is going to really stick these two ammonia molecules together. All right, let's go ahead and clear the screen and do our next one. Okay, let's go ahead and look at this one. This one is methane. So looking at methane, my carbon has 4 bonds, and so I'm going to attach the 4 hydrogens to them. Okay, we drew 2 of them. Our next step is to determine if these are polar or nonpolar. And looking, we see that these molecules are symmetrical. So I have the same bond going all the way around a central atom, and there's no differences there. So this is nonpolar. Okay, so what's holding 2 nonpolar molecules together? And the answer is dispersion. Is there anything else? Do I have dipole-dipole, hydrogen bonding? And the answer is no. You don't have any of those because this is nonpolar. So when you have nonpolar molecules, dispersion forces are the only thing that's holding it together. So this is your strongest intermolecular force. And so sketching out your dispersion force, so I'm just going to kind of run the dispersion force between the 2 molecules. Again, you'll have a shifting of the electron cloud. We don't know exactly where it is, but maybe it shifts more to positive over here and negative over here, and that causes a chain reaction with the next molecule, and you'll have a shifting of electron cloud. And then the next split second, all of this goes away because maybe this one shifts to a plus charge, and so then we have a shifting throughout the whole material. That's a little bit negative here, this one will become a little bit positive here, and then this one will become a little bit negative here. So, and this happens just really quick. So, and that is what's holding this molecule together in a solid or a liquid. If it's a gas, it doesn't have any of these intermolecular forces. It's just independent and it will stay nonpolar. But in a liquid or a solid, these shifting dispersion forces are what's holding the molecule together. All right, we have one more molecule to go through, and that is hydrogen fluoride. Now, if you look at this molecule, it just has one bond. So really I can look at it as a bond or I can look at it as a molecule. And when you remember, for nonpolar bonds, it should either be bonded to itself or it should be a carbon-hydrogen bond. So those are the only 2 situations that you should have for a nonpolar bond. Well, do we have anything bonded to itself? No. Do we have carbon and hydrogen? No. So this is a polar molecule. So remember, with polar bonds, you can draw the little arrows that show where the charge is. So I know around my fluorine it's going to be negative, around my hydrogen it's going to be positive, and um, I can determine that these are polar molecules. All right, what is holding polar molecules together? So the very first thing that should come to your mind is dispersion, because everything has dispersion, or these shifting electrons, electron clouds that are causing a polarity. The second thing, because I have polar and polar, I have dipole-dipole. And last but not least, I have hydrogen bonding. Anytime you have dipole-dipole, you should double check and see if you have hydrogen bonding. And remember, hydrogen bonding is not a bond, but it's an intermolecular force. And so when I look at this list, what is the strongest stickiness between the two molecules? And that would be the hydrogen bonding. All right, let's do one more example, and I'm just going to do that third example. So I have, this time it's not bonded to itself, but it's bonded to something different. So let's look and see what happens when we have kind of a mix-up here. So here's my water, and I just kind of drew it on the side there. And then let's look at our carbon dioxide. So carbon dioxide, carbon has 4 bonds. And so because I just have 2 oxygens I'm connected, these bonds will be as far away from each other as possible. So that's a Vesper theory. Just saying that the electrons in the bond will repel each other. All right, so I sketched out a little molecule geometry there so I can kind of see if it's polar or nonpolar. You should have that water is polar, so that should be memorized. But you can see that it's a bent shape. Bent shapes are always polar. Let's look at this next one. So I don't have any dots around the central atom, and looking at those bonds, I have the same bond all the way around. There's only 2 of them. This is a linear molecule. So this molecule is nonpolar. All right, so let's list the intermolecular forces between these two. So the very first thing that should come to your mind is dispersion, because everything has dispersion forces. The second thing that should come to mind, because it's a polar and nonpolar, I have a dipole-induced dipole. And last but not least, I need to check, do I have hydrogen bonding? Well, let's look at my molecules. Well, first of all, I should have polar and polar to have hydrogen bonding, but let's just kind of double check. So this one has no hydrogens. So because of that, you should have no hydrogen bonding, okay? I do have some oxygens there, but they're not bonded to any hydrogens. Over here, I do have hydrogen bonding, but that would be only bonded if I had 2 water molecules bonded together. And I don't have that here. I just have water bonded to CO2. So I am done. That's all I have. Dispersion and dipole-induced dipole. So the strongest there would be this dipole-induced dipole holding these 2 molecules together. So remember, in a dipole-induced dipole, you have an electron cloud shift. So normally it's going to be spread out evenly, but because of the proximity of the water, you'll see that we have electrons being repelled, and the electrons in the bond are more over towards this other oxygen, and you have a more positive side over here, and that is because oxygen in the water is so negative. And remember, there's those little bare naked protons hanging out, but they do not participate in this scenario as far as the intermolecular forces. All right, so here's a slide that will give you some practice. So go ahead and pause the video and practice out, identifying if it's polar or nonpolar, and then figuring out what are the intermolecular forces in between. Okay, we're back. First of all, we're going to identify if it's polar or nonpolar. Water is polar, and you should have that memorized. And let's look at this next one. So this next one, I see some dot pairs around oxygen, and so that is kind of a signal to me that this is polar also. So it's kind of a bent shape attached to a carbon, and so anytime you have a bent shape, it will be polar. So let's go ahead and do the IMFs. So the IMFs on this first one we have dispersion always. So that's always the first one that you should put down. And next, let's look at our polarity. I have polar with polar. So I will have dipole, dipole. And anytime you have dipole, dipole, let's double check and see if you have hydrogen bonding. So over in water, I have oxygen bonded to a hydrogen. So that should have hydrogen bonding. But let's see, the next molecule also has to have hydrogen bonding in order to have hydrogen bonding in between. And look, I also have an oxygen with a hydrogen. So I will have hydrogen bonding between these two molecules, which is probably the strongest intermolecular forces. They're roughly the same size. That alcohol, that CH3OH, is a little bit bigger than the water, but not by much. And so they're roughly about the same. So you would say that the hydrogen bonding is your largest. All right, looking at this, the ammonia and the ammonia, we've already did this in a previous slide. So this is just good practice for you. So it is a polar molecule with a polar molecule. So as far as the intermolecular forces go, I would have dispersion. I would also have dipole-dipole because it's polar and polar. And then we should check and double check, or we should double check that it has hydrogen bonding. And I have a nitrogen bonded to a hydrogen here and a nitrogen bonded to a hydrogen here. So yes, it would have hydrogen bonding. And this is the same molecule. And so when we rate it, the hydrogen bonding would be the most. Let's look at this next one. So I have oxygen. It's just bonded to itself. And so because it's bonded to itself, it is nonpolar. And then let's look at this next one. We've already determined that it is polar. So in that number 1. So this is nonpolar with polar. So the intermolecular forces, it should have dispersion. And then it should have the dipole, induced dipole. And then we shouldn't have anything else because we don't have two polar molecules, but we can just kind of double check if there's hydrogen bonding. So I would have hydrogen bonding here if this one had hydrogen bonding. And this one does not have hydrogen bonding because there's no hydrogen, it's just oxygen. Okay, so I'm done. Between these two, your dipole induced dipole is going to influence the properties the most.